The third interstellar object ever found shouldn't be shining this way. Instead of a comet's sunlit tail, 3I Atlas glows mysteriously from its front, in defiance of basic physics. Hubble and JWST data say the dust is too thin, the core too small, and yet the brightness rivals objects twice its size. Some scientists, like Avi Loeb, now ask, is Atlas hiding a nuclear heart? If he's right, it rewrites what we know about the cosmos, or exposes how little we understand about the icy relics between stars. So what's the truth behind this forbidden glow? Hubble's first close-up of 3I Atlas didn't show the usual comet signature. Instead of a sunlit tail streaming behind, the brightest part of the coma pointed forward, directly into the oncoming solar wind. The glow wasn't just a trick of perspective. Imaging teams traced the surface brightness profile across the head and found a clear asymmetry. The maximum intensity sat ahead of the nucleus, not trailing in the wake. That's not how sunlight works on comet dust. Normally, the brightest region sits just behind the nucleus, where sunlight hits the densest cloud of ejected ice and rock. But here, the profile peaks on the sunward side, with the glow dropping off sharply behind. The team mapped the phase angle, the angle between the sun, the comet, and the observer, and ran scattering models to see if forward reflection could explain the effect. The numbers failed to add up. Even at the most favorable geometry, the coma's optical depth was too low for sunlight to bounce forward with this much strength. The dust was optically thin, not dense enough to act like a mirror or lens. In fact, the coma's brightness up front would require either a vastly denser dust cloud or a much larger reflecting body than the Hubble images allow. No anti-solar tail appeared in the images, just a faint, steady glow facing the sun. The nucleus, buried in that forward haze, was too dim and too small to account for the observed light by reflection alone. The imaging teams double-checked for instrumental artifacts and tracked the coma over several nights. The forward glow persisted, stable and real. With sunlight ruled out as the main driver, the search turned inward. If the light isn't coming from reflected rays, something inside Atlas might be powering the glow. For the first time, the natural comet model started to crack, and the idea of internal energy, a headlight, not a tail, stepped into the spotlight. Astronomers turned to the numbers. If sunlight alone were powering the glow, the math demanded a body close to 20 kilometers wide, something massive, bright by sheer surface area, impossible to miss in Hubble's sharpest images. But the coma told a different story. The dust cloud around 3I Atlas was optically thin. That means it's not dense enough to reflect much light. Most of the particles were too sparse, too far apart to act as a mirror. The nucleus itself, buried in that haze, didn't show up as a solid, bright point. Hubble's surface brightness profile put a hard cap on its size, no more than 4.4 kilometers in radius, probably smaller. That's less than a quarter of what the brightness would require if the light were just bouncing off rock and ice. Surface brightness measurements from Palomar and Hubble agreed most of the light wasn't coming from a big, shiny nucleus. It came from dust, but not enough to make the coma opaque. The coma's total cross-section, calculated from the observed magnitude, couldn't make up the gap. If you crushed a mountain into powder and scattered it into space, the grains would reflect more light than the rock ever could. But even then, the dust around 3I Atlas was too thin to match the glow. The numbers held, even as astronomers tweaked the assumed albedo, the reflectivity. Whether the dust was dark as charcoal or pale as snow, the required nucleus size stayed far above what the images allowed. Hubble's high-resolution imaging searched for a point source, the telltale sign of a big, reflective core. Nothing. The convolutional fitting techniques, tested on dozens of comets, set a strict upper bound. Nucleus radius under 2.8 kilometers. Ground-based estimates, using standard brightness-to-size conversions, kept coming in high, 10, 15, even 20 kilometers. But those models only work if the coma is thick. Here, the coma was barely a whisper, its particles scattering sunlight, but never enough to explain the full signal. The math didn't budge. Too little dust, too small a body, too much light. The only way to reconcile the numbers was to accept that something else was adding to the glow. Not just scattered sunlight, not just dust. The standard Comet script didn't fit the data, and the case for a hidden energy source, something inside, not outside, grew stronger with every failed calculation. 3I Atlas didn't dive in from above or below. Its entry angle is almost flat, just 5 degrees off the ecliptic, the same plane where every major planet orbits. Most interstellar objects come in at random angles, slicing through the solar system like stray bullets. But this one glides nearly parallel to the planetary disk, retrograde, as if it's tracing the same invisible highway we use to launch probes to other worlds. Statisticians ran the numbers. The odds of an interstellar object arriving this close to the ecliptic by pure chance are about 1 in 500. That's not just rare, it's almost unnatural. The ecliptic is a thin slice in a vast three-dimensional sky. If arrivals were random, most would miss by tens of degrees. Yet here, the inclination is 175.1 degrees, just 5 degrees shy of a perfect flat pass, but moving against the flow. This alignment isn't just a geometric curiosity. It sets up a sequence that steers 3I Atlas past Venus, Mars, and Jupiter, almost as if it's sampling the solar system's main attractions. The trajectory isn't a crash or a scatter, it's a tour, laid out along the same corridor our own spacecraft follow when they need to visit multiple planets. Space doesn't do symmetry, not naturally. But every calculation, every model, keeps circling back to that razor-thin plane. And in a solar system built on orbits, that's the one path where you see everything. Mars gets the closest look. On October 3rd, 3I Atlas will pass just 0.19 astronomical units from the red planet, about 28 million kilometers. That's closer than any other major planet during its run through the inner solar system. For a few hours, Mars-based orbiters will have a direct line of sight, while Earth is already losing the object to the sun's glare. But the window doesn't last. By October 4th, the object drops below 25 degrees elongation from the sun, as seen from Earth. By October 21st, it's only 2.6 degrees away, completely lost in the solar haze. Perihelion comes on October 29th at 1.36 astronomical units from the sun, hidden from every telescope on Earth. The blackout lasts until early November. By the time 3I Atlas reappears, it's already outbound, dimming, and accelerating away at nearly 150,000 miles per hour. Intercepting it isn't just hard, it's nearly impossible. The required delta V for an Earth-based mission is at least 24 kilometers per second, far beyond what any chemical rocket can provide. Even Mars departure windows, which could have shaved that number down to 5 kilometers per second, are already closing. The only plausible spacecraft intercept, using Juno at Jupiter, would need a perfectly timed maneuver and would still only bring the probe within 27 million kilometers of the target. Every hour, the gap grows. No matter how fast we react, the object is always one step ahead, and the chance to catch it slips away with every passing day. Spectrographs aimed at 3I Atlas caught more than just scattered sunlight. The signal split into a fingerprint of ancient materials, water ice, silicates, and complex carbon molecules, the same blend found in the oldest meteorites. But the chemistry wasn't the only surprise. The spectrum matched Tagish Lake meteorite dust mixed with water ice grains about 10 microns across. That's a recipe older than the sun, forged in the cold before our solar system formed. The surface told its own story. Hubble's images tracked dust streaming from the sunlit side, but the numbers stayed low. Mass loss rates hovered between 12 and 120 kilograms per second, depending on the size of the dust grains. Over half a year, that adds up, but not by much. Even at the high end, the surface would lose just a few centimeters, far less than the meters most comets shed as they near the sun. Some ground-based teams calculated even lower rates, closer to a single kilogram per second, hinting at a crust that's barely eroding at all. Thermal models ran the numbers. The coma looked warm, but not wild. No jets, no violent outbursts, just a steady, low-key haze. The water ice stayed put, barely sublimating, while the dust cloud remained optically thin. Not enough particles to scatter much sunlight, not enough heat to drive a classic comet show. The material was old, the surface was quiet, and the energy budget didn't add up. For a body this ancient, the warmth was out of place, and the erosion was almost an afterthought. Harvard astrophysicist Avi Loeb looks at the numbers and sees a different answer. Instead of a dying comet, he proposes a working reactor. 10 gigawatts of steady power, hidden inside a shell of ancient dust. That's not a metaphor. That's the energy budget needed to match the coma's brightness if sunlight and outgassing are off the table. The math is simple. The coma glows with the intensity of a city's worth of power, but the dust is too thin to act as a mirror, and the nucleus is too small to be a beacon by reflection alone. So, Loeb asks, what if the light is coming from within? Not from the sun, but from a nuclear heart, radiating heat through a thin crust of interstellar material. This isn't just speculation. Loeb's model makes predictions. If 3I Atlas is powered by a nuclear source, the brightness should hold steady as it swings through the inner solar system, indifferent to its distance from the sun. No comet does that. The coma's glow would be constant, not flaring up as solar heat rises, not fading as it speeds away. The energy output, about 10 gigawatts, would dwarf anything natural at this size, far outpacing what radioactive decay or solar heating could provide. And if this is true, then what we're seeing isn't a comet at all. It's technology. The kind that's built to last, to travel, to observe. Loeb's hypothesis is bold, but it's not immune to testing. If the glow dims with distance like a normal comet, the nuclear idea falls apart. If the emission remains stubbornly steady, then the mystery deepens. The next round of observations, by Mars orbiters, by Juno, by any telescope that can catch a glimpse, will tip the scale. For now, the possibility hangs in the balance. A nuclear-powered visitor, hiding in plain sight, waiting for the data to decide. Hubble and JWST data confirm that 3I Atlas emits a steady, forward-facing glow, with optically thin dust and a body size measured at 4 to 11 kilometers, far too small to reflect enough sunlight for its observed brightness. Over 6 months of tracking, surface loss has remained below 1 millimeter, and spectroscopic analyses reveal ancient water ice, silicates, and organic molecules, all at unexpectedly warm temperatures. The object's trajectory, just 5 degrees off the ecliptic, passing near Venus, Mars, and Jupiter, matches the flight paths used for human-made probes, with its closest approach hidden behind the Sun on October 29, 2025. Key questions remain unanswered. The true source of 3I Atlas is energy, and whether its path is evidence of intent or coincidence. What is clear is that 3I Atlas challenges current comet models, and for now stands as one of the most puzzling objects ever observed entering our solar system.